Thank you for the introduction. In this presentation, I'm going to introduce our spatial light modulator, in which we call it the EXULUS. You will see some of the basic principles of a spatial light modulator, details of our products, some examples and demos of what we can do with it. So here we go. The spatial light modulator, or SLM for short, is built upon the technology called liquid crystal on silicon, or LCOS. This is borrowed from the microdisplay fabrication process, which is by itself a very mature process. For example, you can find microdisplays in overhead projectors for conference presentations or in movie theaters. Our SLM panels are reflective type, which means that when you use it, the light source is incident normally on the SLM panel and is reflected backward. The figure here is the basic elements within the SLM panel. Starting from the top, we have this protective cover glass, which is usually coated with anti-reflective coating. On the bottom of the glass, we have a transparent electrode layer, which is usually ITO. And then we have this alignment layer, and then this is the space where the liquid crystal fills in. On the bottom, we have very much the same feature. We have this alignment layer and then the electrode layer. The purpose of the two alignment layers is to provide the liquid crystal molecules an initial uniform orientation. For example, in here, all the molecules are lying flat to start with. The top and bottom conductive layers connect to the driving signal. The difference here is that the bottom layer is patterned into small and individual pixels. This way, each electrode is driven separately, forming the individual pixels of the SLM itself. As we said, this is a silicon process, so the last layer here is a silicon backplane. There are some cases that there is a dielectric layer in between the alignment layer and the bottom electrode layer. This dielectric layer is used to enhance the reflection for a particular design wavelength. Since most of the optical power is reflected rather than absorbed, this can also improve the power handling of the device. As the voltage is applied across the two electrodes, an electric field starts to build up in the liquid crystal layer. It causes the molecule to experience a force and try to rotate or align into the direction of the electric field. So this somehow counteracts with the predefined alignment from the alignment layers. Hence, the molecules start to point upwards, like this here. As the voltage continues to increase, it will eventually dominate the force and finally pulling all the molecules upwards. Now, if we reduce the voltage, the anchoring force from the alignment layer kicks back in again, and the liquid crystal starts to rotate back until they are all lying flat again as the voltage drops to zero. Looking from the top, the SLM is arranged into a grid array of pixels, where each one can be addressed or controlled by itself. The bottom left figure here is an actual SLM when you see it under the microscope. The liquid crystal itself is actually a retarder. The orientation that we talked about just now is also referring to the slow axis of such retarder. The alignment layers ensure all the slow axes of each pixel are in the same directions from this view. The orientation of the liquid crystal molecules corresponds to the amount of retardance of a phase, or if the incident beam's polarization is aligned to the slow axis of the liquid crystal, it can also refer to the actual optical path that it travels. As the liquid crystal molecules lie down horizontally, it corresponds to the longest path, and vice versa, it is shortest when the molecules stand up. For most SLM devices or applications, the total phase or retardance range required is about 1 wave. As you can see from the figure on the bottom right here, for a plane wavefront that comes into the SLM with such a molecule or signal arrangement, the reflected wavefront looks something like that. And so you can see that from regions where the molecules stand up, the reflected wavefront actually goes faster than those that lie down. And the difference here is just about 1 wave. What you see here is the entire product line of our EXULUS spatial light modulator. The first that we would like to talk about are the EXULUS HD1 and 4K1 units. They share the same form factor, they have the same wavelength range, which is from visible to near infrared, that is about 400 to 850 nanometers. The main difference is their resolution, where HD1 is 1920 by 1080 and 4K1 is 3840 by 2160. The pixel pitch, or the size of pixel, is 6.4 micron for HD1 and 3.74 micron for 4K1. That makes the overall dimension of the panels about the same for the both units. These SLMs connect to the computer by HDMI, so they follow the standard 60 frames per second frame rate for HD1 and 30 frames per second for 4K1. Our SLMs are designed for Thorlabs mounting options, therefore you can directly connect 30mm cage systems in front of the panel, or you can also do post mounting from the bottom or from either side of the unit. Now there are some more little features around. For example, the two knobs up here are used to control the tip and tilt angles of the panel. With the 4K1 unit, we also have a trigger out signal so that you can use the SLM to synchronize other equipment. With the HD1 unit, we also have a feature called frame boost mode. What it means is that it expands the 3 primary color channels from the video signal and send them to the SLM panel in such sequence. So essentially, the 60 frames per second signal contains 180 frames per second information. Now all these units are pre-calibrated at 633 nanometers, which means that the phase stroke is 633 nanometers. If you need to use it with other wavelengths, especially longer wavelengths, we can also pre-calibrate to such wavelength before we ship it. Also, if there is a need to have the panel extended from the main unit instead of integrated in such form, we can also do that too. So please reach out to our technical support for these customizations before you place the orders. These are the actual units of the device. The panel is on the front with this protective cover. You can take the cover off and store it on either side of the main body. We have this bundled thumb screw for adjusting the tip and tilt of the panel. To lock the setting, you can use the collar here. On the back of the unit, we have all the connections, power, HDMI, and USB. And with the 4K1 unit, we also have a trigger out signal. These are the EXULUS HD2, HD3, and HD4 series. Again, they have the same form factor, which is much more compact, and the difference is their wavelength ranges. HD2 follows the same range as HD1, 400 to 850 nanometers. HD3 goes deeper into the IR, so that is 650 to 1100 nanometers. EXULUS HD4 is a special version with dielectric coating and is designed only for 1550 nanometers, which is the communications wavelength. Their resolutions are close to HD, but it's actually 1920 by 1200, more precisely called WUXGA. They have 8 microns pixel pitch, and they also have the HDMI connection 60 frames per second. Again, these units are designed for Thorlabs mounting option, so they have the 30mm cage in front of the panel, as well as post mounting. They also have the tip and tilt adjustment for the panels, and all these versions come with trigger out signal. Again, if there is a requirement for wavelength calibration, we can do that. Otherwise, by default, HD2 is calibrated at 633 nanometers, and for HD3, it is 1064 nanometers, and of course, 1550 nanometers for HD4. Just like the HD1 and 4K1 units, there is this protective cover on the front, and this time you store it at the back side of the main body while it's in use. The tip and tilt controls are now on this side, and all the connections are now on the top. Again, we have the power, HDMI, and USB, and all these versions come with the trigger out signal. We extend the HD2 and HD3 into the HP series, where HP can stand for high performance or high power. We add liquid cooling capability to these units so that you can connect to a liquid chiller, for example, Thorlabs LK220. Now, doing this allows any heat that is generated on the SLM panel due to absorption of the incident beam is being directed away. And so this panel can handle much higher optical power. And because of the temperature stabilization, this unit's operation is also more stable than the standard units. Again, we have the wavelength range as 400 to 850 nanometers for HD2 HP and 650 to 1100 nanometers for HD3 HP. Now, these units are designed in a way that you can have the panel mounted directly on the main body as an all-in-one format, or you can have the panel extended out from the main body as what we call a panel separated format. Again, these units are post-mountable, and if there is any wavelength calibration that is needed, we can do that. Also, if there is a requirement for HD4, the 1550 nanometer unit, to have the same form, we can do that too. So this is the all-in-one format where the panel and the adapter boards are mounted on the main body directly. And this is the panel separated format with the adapter board and panel laid out this way with post mounting. The panel is also compatible with Thorlabs kinematic mounts. For example, here we have a Polaris behind so that you can also control the tip and tilt of the panel. And we should all know by now that the SLM deals with phase. So it can produce the same effect as other devices that also relied on phase. For example, in a diffraction grating, it tilts the beam because of the periodic phase gradient pattern. And for lens, you can also think of it as the phase shifting device, where the path that travels on the center is the longest and gradually decreases along to the edge of the lens. We can also generate a vortex beam in which the phase increases asymmetrically around the center, like the bottom left figure here. The output looks like a donut, or what we call a donut profile. And recently there is an increasing interest on producing an error beam. These are beams that travel without any distortion. The way to generate an error beam is by something called a cubic phase pattern. Now I'm going to demonstrate how to generate a vortex or error beam with an SLM device. We start off with a helium neon laser here, which is 633 nanometers. We have a polarizer and a halfway plate assembly for polarization control. The mirror here reflects the beam onto the SLM unit. We have an HD2 here. The output of the SLM goes straight to a CCD beam profiler, and we take part of the beam and project it to a whiteboard as well. So let's see how we do it with the software. We have the HD2 connected. On the bottom left here, we have 4 different tabs of SLM control, and let's choose pattern here. Now we're also looking at the beam profiler screenshot and another camera view of the whiteboard. Let's choose the vortex here. And by default, we have a 633 nanometer and order of 1 vortex. And let's see how it looks like. Now we have a so-called donut beam with a hole in the middle. So that's the order 1 vortex beam. Notice that the phase pattern of a vortex generation is a radial pattern with the singularity center in the middle. It's very important to have your incident beam that lands on this very center. So let's say if we misalign the beam, you will notice that the vortex pattern disappears. So it's very important to have your beam which is on this very center of the SLM unit. And similarly, if the polarization of the incident beam is incorrect, let's say if we change it with the halfway plate here, you can notice that the vortex beam changes back into a normal Gaussian beam. So it's also very important to have the polarization of your incident beam to be aligned with the slow axis of the liquid crystal as well. Now let's do a higher order, let's say order of 10. We have a phase pattern like this, and the vortex pattern looks like this here. We have a much bigger ring and a much bigger null in the center. So let's move on to the area beam. As we said before, we need a cubic phase pattern for an area beam, and this is how a cubic phase pattern looks like. Now, in order to see enough effect on the whiteboard or the beam profiler, we need a much larger alpha. So let's bring it up to 100,000. And let's see how it looks like. So this is how the phase pattern looks like, and this is how the area beam would look like. Now the demo that you have just seen is only some of the very few applications of a spatial light modulator. There is a lot more behind that. If you think of the phase pattern on the SLM panel being projected to a far field, we are essentially doing Fourier optics. In this case, we can do a very interesting trick of projecting almost anything by simply working out the relation of the image and its Fourier transform pair. Of course, we need to be very careful as we are only working with the phase during this transform, but in principle, it can be done. And it is actually the most general form of the beam manipulation when we use an SLM, literally by dealing only with the phase. We call this computer-generated holography, or CGH. There are many approaches on how we can calculate the phase pattern for CGH. In fact, the CGH algorithm itself is one of the very major academic research topics. Our software and SDK provide the capability of CGH generation using some of the most straightforward approach. We start off with the image that we wanted to project. Although the panel is in HD or 16:9 aspect ratio, the image that can be processed is still a square. This is because of the nature of Fourier transform. The aspect ratio of the final image depends on the shape of pixels, not the aspect ratio of the whole screen. In this case, the shape of pixel is always square. Now, we crop and resize the input image in order to suit the panel dimension as the input of the CGH algorithm. We Fourier transform it, we extract the phase part, and then we scale it to the grayscale of the image. That is what we send to the SLM panel. We can also inverse Fourier transform our result and compare to what we have in the beginning. And then we iteratively refine the result, and in most cases, we only need a couple of iterations, and that is good enough to produce the most optimized output. So that is the basic idea of the CGH algorithm that we use. Of course, there are some more complex processes within, but we are not getting into those now. If you have your own method of doing this, you can also directly send your result as a standard image in the software. Now I'm going to demonstrate CGH generation and projection. We need to have a wider beam so that we can illuminate more pixels on the SLM. And that's why we'll choose a CPS laser here with 532 nanometer. Again, we have the mirror to reflect the beam onto the SLM. And this time we project straight to the whiteboard, which is more or less like a far field. Okay, so let's see how we do it with the software. Again, we have this interface here, and let's choose the CGH tab. We load in an image file, and let's choose our favorite mascot. If the image is too large or too small, we have the scaling option for you. And notice again that in the preview window, we can only process square images. And also notice the colors of the black and white, where black means no light and the white means where we want to have the laser projected on. And this could be sometimes very confusing, so that's why we have this invert image features in case if the image itself is not correct. So what we wanted is actually this one here. change to 532 nanometers, and the focal length being the distance of the whiteboard, which is about 450 millimeters right now. Now we have this calculated CGH pattern on the SLM, and let's see how it looks like. Okay, so now we have this stock being projected onto the whiteboard. Notice that there is a very bright center spot here as well. We call it the zero order spot. The zero order spot comes about because of the limited fill factor of the pixels on the SLM panel. And it comes from the unprocessed area of the panel. We do have a trick to reduce this bright spot, which is by reducing the focal length to, say, 250 millimeters. And let's see the result. We have the dog being blurred, and that is because the image plane has been moved forward. But the center spot has not been changed. And what we can do now is to put some more imaging lenses here to re-image this dog onto the whiteboard. And as you can see, the zero order spot has been defocused. And this is how we reduce this spot with a bit of expense of the contrast of the CGH image. And most of the time, the size of the image could change as well. So there will be quite a lot of adjustment as well. So here are some more applications that you can use with the SLM. Some of the interesting ones include, for example, the left one here. We have a multi-point tweezer in which the SLM is manipulating a few particles in the tweezer device. And by manipulating a beam around, we can also use it as a laser writing device. The vortex that we saw before, it is actually a fundamental element for what we call an STED, the stimulated emission depletion imaging, which is a form of super resolution imaging. Again, because the SLM manipulates wavefronts, it can be used with adaptive optics, beam shaping, these kind of applications. And with the high power series, it can also handle some more industrial applications such as multi-beam steering, lithography, laser writing, etc. Okay, so these are what we would like to share in this presentation. Thank you for your attention. I would now like to answer any questions you may have.